Hey everybody, I hope you all are still staying safe and healthy. Whew, yeah, it's one of those days already. Alright, so, we're still continuing some new stuff. We are moving on to 5.12. So this is the last unit of the last section of Unit 5. Alright? So what does that mean for like testing? At this point, I'm going to be honest, I'm not exactly sure how we're going to be doing testing, but I'll figure it out, okay? And so, for now, just focus on getting these modules done. So, 5.12 is Cavalieri to the rescue, okay? Obviously, Cavalieri is a name of a famous mathematician in the past, and we're about to learn his principle, all right? So, we've got three people, or some of our favorite people here. Carlos, Clarita, and Zach are playing a geometry game, and I know how much you guys love geometry games. Each player selects a point C on the line segment MN, so this is MN, and they select different C's along it, okay? The player who creates the points A and B form the vertices of a triangle, okay? So vertice, and then the C's are the other vertice, okay? The player who creates the triangle with the largest area wins the game. They must be stuck in quarantine as well, because I don't know if I would ever come up with that type of game, especially a geometry game. But regardless, they've got this game, they're picking points, they're choosing which triangle has the largest area. At least they're trying to figure out which one would have the largest area. Carlos has placed his point at C1, way over there. Clarita has selected hers at C2, and Zach has chosen to locate his at C3. Now they are discussing their choices before calculating the areas of each triangle to determine the window. Okay, I'm going to try different voices here, alright? Carlos, I choose my point, so the triangle would stretch as far left as possible, enclosing a large amount of area.
Clarita, I thought it would be best to create an isosceles triangle, so the triangle would be symmetric about its altitude. So I chose a point on segment NN directly above the midpoint of segment AB.
Zach, I thought that a right triangle would create the largest triangle, since my triangle would be half a rectangle. Alright, so that's their justification for the different points that they did. Without doing any calculations, who do you think created the largest triangle? Right? And, you can look at your page, you can look at this guy. Which one is the largest? What do you think? That's what question one's asking you to do. Question two. If you're playing the game with Carlos, Clarita, and Zach, where would you place the point C? Mark a point on the segment MN to represent your best guess. You may mark your point at the same position as one of those as one that has already been chosen if you agree that point would form the largest triangle, okay? So you've got to figure out some point along here that you think would create the largest triangle. If you think it's one of those points already, feel free to indicate that as your point as well. Now is the time to determine a winner. Make any measurements necessary to calculate the winner of the game. Whose strategy won? Okay, so this actually wants you to grab a ruler or some other measuring tool and measure do some measurements to find the area of these triangles, okay? So, for sure you'll need to measure A to B. Okay, this is our base for all these triangles, okay? But when we're considering the area of a triangle, the area is 1/2 base times height, right? So you need to know the base, and you need to know the height, okay? Well, the height for this one would just be its other leg, right? The height for C2 is going to be the altitude, right? Altitude goes from one vertice and makes a 90-degree angle with the line opposite it, right? But what about this guy? It's not like we can make an altitude and make a 90-degree angle. What happens here, is that you kind of have to imaginary extend this line out and then extend this line out. And that makes a right angle. And whatever this distance is your height. Okay? So, figure out the heights for all of those and figure out the bases for all of those. Put them into the 1/2 base times height formula. And what do you get? What do you find? You might want to pause the video here while you do those calculations because I can't really move forward unless you've done those calculations. Okay? So pause here just for a moment. Pause. If you're hearing this now, I'm assuming that you've already done this, done the calculations. So, next part says, Carlos, Clarita, and Zach were initially surprised by the results and wondered why the triangle images were so deceptive. They began to wonder if they could really believe their calculations. Then Carlos suggested an experiment. He drew a series of line segments in each triangle, with each segment parallel to the base of the triangle, AB, and with corresponding segments in each of the triangles drawn at the same distance above the base, as shown in the diagram below. Carlos then measured each of the corresponding line segments. Okay, so, spoiler alert, all 3 triangles have the same area. What? How? Like, they all look completely different. That's what they're going to be figuring out. So, Carlos thinks he can explain this. So, let me grab my erasing shirt. I'll erase this. So basically what Carlos is doing is he's saying, I'm going to draw a line parallel to AB. Okay, it's parallel to AB. That's going to cut each of these triangles. Oh gosh, let me make sure I do this right. Okay. And so wherever it goes through a triangle is actually going to be one of our lines, right? Okay. So, and he did a few different ones. So let's do one more up here, kind of the... So like this line, and that line. Okay. So, complete Carlos's experiment by measuring each of the corresponding line segments. So again, take your ruler or whatever measuring tool you got and measure each of these segments and compare them. Okay? And as you compare them and as you measure them, you'll start to see why these triangles are equal, okay, in area. Clarita's voice. Okay. Clarita said, it feels like you're treating each triangle as if it were made up of a bunch of layers of slices. Zach, inspired by Clarita's comment, pulled a handful of pennies out of his pocket and stacked them to form a cylinder. I can calculate the volume of the stack of coins using the formula V equals BH. But what if I tilt the stack so it looks more like the Leaning Tower of Pisa? Now how do I figure out how much space the coins occupy? Carlos and Clarita smiled at Zach's clever way of illustrating the idea. That was new to both of them. They were excited to tell a geometry teacher about their discovery and Zach's principle. They were surprised to hear that Zach wasn't the first person to think of it, and that it was known as the Cavalieri principle. Okay, so pause. Cavalieri principle. Let me just give you an example. Okay. Okay. We've got 5 books. 6. Sorry. 6 books stacked together. Okay. These are calculus books. You can look forward to using these when you get to pre-calc. So you got 6 books stacked together. And what would the volume of this stack be? Well, it's length times width times height, right? Or you could do the length times width times height of a single book and multiply it by 6 because there's 6 books, right? But then, what if, let's try, there you go. So now, what's the volume? It hasn't changed, right? It's the same 6 books, they're just tilted. So that's what Zach was trying to do with his pennies there, is that when you've got a prism or a prism or a cylinder for that matter, if you tilt it, then all the stuff, all the volume is still there. That stack was still made out of 6 books. It was just in a different location. So that's why visually or physically we can see that Cavalieri's principle works out. It's still the same slices, which when you measure these out, you should see how that works out. In your own words, state what you think Cavalieri's principle is based on the triangle experiment and the stack of coins illusions and my stack of book illusion, if you want to. So write in your own words what you think it is. Try out another experiment with Cavalieri's principle. Once again, line MM. So we're going to take our eraser, we're going to erase all this stuff in the middle. Okay. So, got line M, it's parallel to line AB, or segment AB. Measure the length of segment AB, and then mark a congruent segment CD anywhere on line MN. Okay, so it's basically saying, measure this length, take it up here, put it somewhere else. So, if I make, mark that as 1 point. So it's, roughly right there. Again, you'll be more precise since you'll actually have rulers and things like that. But you'll measure it, and then you'll mark that same distance up here on MN. Mark another segment EF on line MM so that EF is also congruent to AB. Connect the endpoints of segment AB to the endpoints of segment EF to form another parallelogram. Okay? And also to CD. So it wants you to do this twice, and then you're going to connect the points so that it creates a parallelogram. Okay. So I've just done it once here, but again, on yours, you should have 2, just in different places. Okay. Use these 2 non-congruent parallelograms. Non-congruent parallelograms to illustrate Cavalieri's principle. What can you say about the areas of these 2 parallelograms and what convinces you this is true? Okay, so based off of the stuff that we've already done and the 2 parallelograms that you form here, they're non-congruent because their angles are different, right? Or they should be. What can you say about their areas? Okay. You might even want to use the formula for the area of a parallelogram, which is base times height. Okay. While Zach's demonstration with the pennies has convinced Carlos and Clarita that the volume of prisms and cylinders where the parallel slices are not directly above each other is the same as the corresponding right prisms and right circular cylinders, they are wondering about pyramids and cones where the vertex of the cone is not directly above the center of the base. How do you find the volume of these types of pyramids and cones? Looking online, they have learned that these types of solids are called oblique prisms, oblique pyramids, oblique cylinders, and oblique cones. Okay, so you might want to write these down in this section or in your notebook or something along those lines. But, if you've got this would be a right prism, okay? Where everything is in right angles, okay? This would be a right cylinder because this line forms a 90-degree angle with the base, okay? Right cylinder. Right circular cylinders, I'm sorry. They're not ovals, they're circular. Then we've got oblique prisms, oblique pyramids, oblique cylinders, and oblique cones. Okay, so oblique pyramids or prisms are going to be. Ooh, I don't know if that's. There you go. And I know this last line isn't quite there. You go. Okay, so this would be an oblique rectangular prism. Okay, so it's tilted, sort of like the books were, right? So this is oblique. Oblique prism. Oblique pyramid. So we dealt with pyramids in the last unit, 5.11. If we've got a pyramid that looks like this, where the center isn't right above the center of the base, okay? This would be an oblique pyramid. Oblique cylinders, again, similar to that. You've got your circle, you got your circle like that. This is an oblique cylinder. And then last but not least, our oblique cone. Similarly, you're going to have that and a point. This would be an oblique cone, where the center, where that top point is not over the center of the base. Okay. So, oblique cone. All right. Right prism, right circular cylinder, oblique prism, oblique pyramid, oblique cylinder, oblique cone. Okay. So again, you might want to do your own drawings or print out examples or something like that, just so you can become familiar with what these look like. So while online, Carlos found this information. The volume of a right prism and right circular cylinder is given by V equals base times height, where base is the area of the surface that forms the base, and h is the height of the prism of the cylinder. The volume of the pyramid or cone is 1/3 of the volume of the prism or cylinder with the same base and height. Okay, so with a rectangular prism, right, your base is going to be length times width. So you're going to have length times width times height. That would be that guy right there. For this, the base is a circle, so you're going to do the area of a circle, which is pi r squared. So pi r squared times height. That is that one right there. Okay. And then if you had right pyramids and right cones, okay, I didn't draw those up here because I didn't mention them, but look back in either the homework of 5.11 or the module of 5.11, and you'll see what they look like. But the volume for those is just going to be 1/3 the prisms or cylinders that have the same base area and the same height. Okay, so V equals 1/3 base times height. 1/3 base times height. Okay. So those are the example. That's the definitions that Carlos found online. Clarita found this information. The volume of a prism or cylinder is given by V equals base times height, where base is the area of the congruent cross sections parallel to the base, and h is the height of the prism. The volume of a pyramid or cone is 1/3 of the volume of a prism or cylinder with the same base times height. Okay. So, if we're looking at these guys, right, it says the volume is base times height with base equaling the area of the congruent cross sections parallel to the base. So, if we're looking here at this oblique cylinder, this is our base. That would be a congruent cross section, right? So whatever that area of this space is, which should, if it's congruent to both of the bases, right? So base is is equal to the area of a cross section that is congruent to the bases. So just calculate the base and multiply it by the height of the prism. So from there to there, this is height. Okay. Essentially, if you think about it, again, going back to our book, I'm just going to do 3 this time, so it's not as heavy. So if you got your oblique prism here, if you can find the area of one of these slices and then find the height, it's essentially like you're pushing everything back together so it's straight again, like you're doing the same as you would do for the right prism. Okay, so just be careful, right, if when you're doing your homework and such, the distance from here to here, right, this full line right there, that does not equal the height. Okay, the height is from the top base to the bottom base straight down, as if it was a right angle. Just be careful about that. Number 7 states, how do these two statements differ and what do those differences imply? Okay, so how do they differ and what does that mean? Last but not least, Carlos, Clarita, and Zach each find interesting GeoGebra animations and activities that give them additional insights about Cavalieri's principle and the volumes of oblique pyramids and cones. Okay, the whole next section that leads up to question 8 does require you to go to these websites that are there. I know that not everybody has equal access to the internet at this point, and so I'm not going to require problem 8. I would still heavily suggest it, and if I remember, I'll put these links in the description of this video. But it's not required. If you do it, I'll give you extra credit. There you go. So a little bit more of extra credit opportunity, but it's not required. So if GeoGebra just doesn't work on your computer, if you don't have enough time to access them, don't worry about number 8. I require 1 through 7. Okay. I just wanted to finish up by saying that's it for 5.12. Okay, which means we're done with Unit 5. Again, I'll let you know what we're going to be doing about tests here in the next week or so, because that's a bridge that we're going to have to cross here soon. But just to review, the Cavalieri's principle basically means if you've got a shape that is not right, not a right cylinder, not a right prism, not a right triangle or whatever, but it has the same base area and the same height, then ultimately they're going to have the same volume. No matter how tilted they may appear, they're going to have the same volume or area. If you have any questions, please feel free to ask me on Classcraft or via email. And until then, stay safe, stay healthy, and keep learning. Bye.